video we'll solve this example. I have a plane in R3. I want to look at projection on it using the regular dot product. That's going to determine what's perpendicular, what isn't. So I'm going to start by finding an orthogonal basis for W. We don't really have a recipe for that yet, so I need to use our knowledge of R3. In fact, I think there was a question like this on last term's final for NYC. So I have x plus y minus z equals 0. If I'm just trying to find any basis, I have a system. It's already reduced, so I'm going to use s here, t here, so I get that x is minus s plus t, y is s, z is t, so I'm getting those vectors form my basis for W. Alright, perfectly fine basis for W, not orthogonal at all. If I take the dot product, I'll get minus 1, not 0. So I need to use geometry to find an orthogonal part. And so I have one vector, which I'll keep, minus 1, 1, 0. I have a second vector. That's not good enough because it's not orthogonal. Let's make it even more obviously non-orthogonal. So this is 1, 0, 1. So I need to find something orthogonal. And so what I'll use is I'll use our good old-fashioned projections that we've used before. I'm going to take the orthogonal component. So let's call this V2. Let's call this V1. So my V2 is 1, 0, 1, this vector, minus its projection on V1 of 1, 0, 1. And so that's 1, 0, 1 minus 1, 0, 1 dot minus 1, 1, 0 length of minus 1, 1, 0 squared, well, V1 again, so minus 1, 1, 0. Alright, so we're taking away the part that's along V1 to make sure that they're actually orthogonal. Alright, so I get 1, 0, 1, minus 1 over 2, minus 1, 1, 0. So I'm going to get 1/2. I'm going to get 1/2. And I'm going to get 1, 1. Alright, so the orthogonal basis will be my first vector, which I haven't changed. That one was fine. And then I had to change my second one to make sure it was orthogonal. So I removed the part that was along and I got the orthogonal complement, and that's my orthogonal basis for W. Let me double check that I have the same one in my notes because I'll have to erase it in a second. All right, so I could use this. Let me double check. I think I'm using a slightly different one. Yeah, so you can use this. One thing I could do as well is stretch V2. So I could also use, to get rid of the constants, I could use minus 1, 1, 0, 1, 1, 2. So I really just took V2 and doubled its length to ensure it didn't have any fractions. Both are fine, both will give you the same projections in the end. Alright, so B, find an orthogonal basis for W perp. Well, I need to find a basis for W perp. I could either use geometry or algebra. Let me use geometry here to save a bit of time. Since we're in R3, we're comfortable with this. W was the plane x plus y minus z equals 0. And so we know that the coefficient gives us the normal vector. So I have a normal vector of 1, 1, minus 1. Well, W perp is also perpendicular, and so it's parallel to n, the normal vector, and so I can take Alright, so this is just a regular basis for W perp. It turns out that any basis will do. Since W perp is one-dimensional, it's just a line, that vector is orthogonal to every other vector in that set since it's alone. Alright, so I have my two bases. And now we're going to try our formula for orthogonal. And so, part C, we had to find, let me take my notes since I've erased everything we had. We had U, which was 3, 4, 1. And I want to find the projection onto W of U, want the projection onto W perp. And then I'm going to check that it works. Their sum should give you U back. So projection onto W view. We're told to take UV1, length of V1 squared V1, plus UV2, length of V2 squared V2. And so in our case, that will be 3, 4, 1 dotted with, actually let's compute them on the side. I think it's going to be too long for this board anyways. So UV1, that's 3, 4, 1 dotted with minus 1, 1, 0. So I'm getting minus 3 plus 4, I'm getting 1. All right, V1 squared is the length of minus 1, 1, 0 squared. And so I'm getting 1 plus 1, I'm getting 2. Alright, U, V2, U is 3, 4, 1. V2 was 1, 1, 2. So I get 3 plus 4 plus 2. I get 9. Alright, and the last number I need is the length of V2. That's the length of 1, 1, 2. So I'm getting 1 squared plus 1 squared plus 2 squared. That's 4, 5, 6. I'm getting 6. Alright, so we're ready to write the projection now. The projection onto W view is 1/2 of V1 minus 1, 1, 0 plus 9/6 of V2, which is 1, 1, 2. So I'm getting minus 1/2, 1/2, 0, plus 3/2, plus 3/2, plus 3. So I'm getting 1, 2, 3. Nice. All right, 1, 2, 3. All right, so if you want to check whether this makes sense or not, you can plug that into the equation for W that we had, which was x plus y minus z. X plus y minus z does give you 0, so at least we got something in W. Now let's find the projection on W perp. Alright, so I need, let's call it V3, so U, V3, length of V3 squared. U is 3, 4, 1, and V3 was 1, 1, minus 1. So I get 3 plus 4 minus 1, I get 6. And the length of V3 squared is the length of 1, 1, minus 1 squared, which is 1 plus 1 plus 1, which is 3. Alright, so the projection on W perp of U would be U V3 over length of V3 squared. So I'm getting 2 times 1, 1 minus 1. I'm getting 2, 2 minus 2. Last thing I want to do is I just want to check that this makes sense. Remember, what we wanted is to decompose U into 2 vectors. And so I found one vector in W, one vector in W perp. I'm just going to check that their sum is in fact U. So the projection was here, 1, 2, 3. The projection onto W perp is over there, so I get 2, 2 minus 2. So on this side, so this is the projection, W plus the projection. And I get 3, 4, 1. And 3, 4, 1, yes, it's U. And so everything is well.